Okay. Can you guys see my screen now?
Yes.
Okay,
Okay.
that's good. That's good. That's good. Okay, so for this reactant molecule here, what is the functional group present that you see, Amanda?
Um. Alkane.
Yep, there's an alkane here, and we have a bromine here, which is a halogen. So we can call this haloalkane. Haloalkane. Right. Another name of that you can see is going to be alkyl halide. Like that. Right. What about the molecule on the right? What functional group do you see on the right?
Amide.
Amide, right? Amide. And be careful, right? Because what if that carbonyl or the carbon double bond oxygen was not there? What functional group would that be?
Amine.
Amine, yes. Amine, amine. Okay. So for synthesis, Elysia, the very first thing I would do is find the similarities. So on the reactant molecule and product molecule, I'm gonna highlight what I see is the same, which is this right here. And then everything else is different. We see in the reactant molecule, there's a bromine here. On the product, there's that amide group right there.
Right.
Right. And you notice how we have an extra carbon right here? That extra carbon right there is gonna be the carbon of the carboxylic acid. Because have you learned about how to make amide from carboxylic acid yet, Elysia?
I'm pretty sure I just didn't do much practice.
Yeah, that's okay. That's okay. So the best way to make the amine is through an acyl halide. Like, have you learned about these other functional groups? Acyl halide, anhydride, and then carboxylic acid.
I think that's what we went over last time.
Is there? Right. Amide, and then nitrile. Right. So this is 118C. I'll go over a 118A problem after this, but you can send me like what topic or problem you want to go over, Amanda. But after I go over this problem, I could go over 118A and then switch back and forth from there. Okay.
Okay.
So all of these here are carboxylic acid derivatives, except for this one right here, because this is the carboxylic acid itself. I'm gonna circle the leaving groups, which are these groups right here. Right? The nitrile, we see there's no carbonyl, so we're gonna call this the cousin of the carboxylic acid derivatives. And the way that I drew it in is in the order of reactivity, right? So going from right to left is gonna be increasing in reactivity, right? And that's because of two reasons. That's because of the leaving group ability, and the other reason is going to be about the...
I think...
Yep, we went over this already.
Oh, yeah.
Carbonyl, carbon. Yep, what was that, Elysia?
Oh, sorry, I'm probably, like, my Wi-Fi's probably slow, but yeah, I think this was, like, kind of what we went over about, like, the reactivity, and then we went a little bit over, like, the naming, and then that's about it.
Oh, right. Of the naming a little bit. This acyl halide here, the most reactive one, can create any of these lower reactive derivatives in one step. Right? So if we want to create, let's say we start with this acyl halide right here, which is an acyl chloride, and we want to create this amide, we can do that in one step. Right? And to do that, we're going to use this amine. And we need at least two equivalents of that, right? Or you need some kind of base, like T or pyridine. NH2 with T or pyridine. Right. So based on that, we can go backwards here, right? We can say that this entire amide right here can come from this acyl halide right there, right? Because we see that this leaving group here can be converted to that leaving group in one step using this amine, which we could draw out like this, NH2 with 2 equivalents, or with T or pyridine. Does that make sense so far, Alicia? Any questions on that?
How were we able to determine
Uh-huh.
like how the Cl goes to or like transforms into like the NH?
Yeah, so we are able to tell that this Cl here transforms to the NHR because we want the NHR in the product. Like that's given to us, right? And because we know that this right here is the amide, which is one of the lowest reactive carboxylic acid derivatives. Like it's like very low in this reactivity ranking list. We can create that amide from the acyl halide, the most reactive carboxylic acid derivative.
Oh, okay, I see what you mean.
Right, because we're going backwards here. This is given to us. We are gonna guess that that came from the most reactive carboxylic acid derivative, which is this acyl chloride right there.
Right.
Right. Okay. Okay. So now this acyl chloride here, like, can come from the parent functional group, which is a carboxylic acid. And this is going to be done by a weird reagent that you've seen in 118A before, which is going to be SlCO2. Does that sound familiar? And you could have that with T or pyridine.
Oh, right.
Right. SlCO2 would convert this OH into this chlorine. So that would convert this carboxylic acid into this acyl chloride right there. Okay. Now, we see that the reactant molecule is this right here, where this is the new carbon, and there's two ways. There's two ways to add a new carbon to the molecule, which that new carbon is the carboxylic acid. Do you know one of those two ways or both of those ways? It's okay if you don't remember.
I want to say Jones.
Also, Jones would come from a primary alcohol. Like if we go backwards right here, right? And we had this primary alcohol, then we could use Jones to convert this primary alcohol into the carboxylic acid, right? Which, if we tried getting from here to here using, let's say, NaOH, right? Like the OH minus attacks this carbon and kicks out the bromine good leaving group in an SN2 reaction, that wouldn't get this because like we won't have that extra carbon right there.
Oh,
right? We'll have 1, 2, 3 carbons coming out of the ring, 1, 2, 3, and then this would have been the OH right there. So we can't get this OH group here like that.
Oh, so we're saying we've added another like carbon to the.
Yep. This right here is the other carbon to the structure, the new carbon to the structure.
Right.
Right. And that new carbon to the structure is the carbon neocarbon of the carboxylic acid right there. Right. And because we started with a primary halocane, there's two ways that she taught you that will add carbon to the molecule, which that new carbon is going to be the carboxylic acid. So I'm going to show you the first way first, which is going to be the Grignard reagent way. So if I put Mg here with ether, do you know what reagent would be formed from this reaction right here?
Well, I know that Grignard reagent adds like substitutes or like it adds like more branches.
It adds more branches, right? This right here would create the Grignard reagent, the RMGBR. Does that sound familiar?
Yeah.
From 118A. This right here is not the Grignard reagent yet. It's just a halocane. Because what is the partial charge of this carbon here? If it's attached to this halocane bromine, is it partial positive or partial negative?
Isn't it partial positive?
Yep, partial positive because it's attached to an electronegative atom bromine. But if you look at this carbon here directly attached to the magnesium, the partial charge is now going to be
Partial negative.
partial negative, which is the nucleophile, right? This is the RMGBr Grignard reagent here. So
Right.
this is what we're going to store as our nucleophile right there, which is going to attack an electrophile. Right. And then once we have the Grignard reagent, we could add CO2, carbon dioxide. But I'm going to draw out CO2 in this Lewis structure because if I draw it out in this Lewis structure, what would be the partial charge of this carbon if it's attached to 2 oxygen atoms like that?
Isn't it partial positive?
Yeah, partial positive because oxygen is more electronegative than carbon. So oxygen is going to pull or withdraw electrons from carbon, making carbon lose negative charge. So it's going to be partial positive, which is the electrophile. So now this partial negative carbon here is going to attack that partial positive carbon, attack the electrophile, which is going to make a new bond between the star and dot carbon. But we can't stop there because like this carbon here would have 5 bonds. 1, 2, 3, 4, 5. That breaks the octet row. To conserve the octet row, yeah, we don't want that. How can we conserve the octet row here?
I would assume that one of the bonds is going to move up to one of the oxygen.
One of the double bonds is going to move up onto the oxygen. So let's say we move this double bond, like one of the bonds there go down to that oxygen right there. So after we do that, we're going to get this right here. The MgBr will dissolve away in the solution. It will disappear into ions. Right.
Okay.
So this would be the starred carbon. This right here would be the neo carbon. Neo bond, I mean. Neo bond between the star and dot carbon. We see that the dot carbon is attached to a carbonyl, which is a carbon of 1 oxygen, and a single bond O minus. Okay. Which is going to be right there. So this would be the answer after we put CO2 without any acid workup step, right? But if you want the neutral carboxylic acid, you could do an acid workup with H3O+, which would protonate this carboxylate ion into the carboxylic acid.
Yeah.
Like that, right? Okay. Now, how many carbons are here, Elysia?
There's 4.
Yep, 4 carbons. How about right here?
5.
5, right. The 4 carbons that you see in the reactant molecule is that yellow backbone right there. This pink carbon here is the new carbon that we added, which came from the CO2 of the carbon dioxide right there. That's right. the new carbon right there. So that's one way to add an extra carbon to the molecule, which would eventually become the carboxylic acid, like that, right? Another way to do the same thing, right, like to get from this haloalkane into this new molecule with an extra carbon and carboxylic acid, is through hydrolysis of nitrile. So let's say we start with the same haloalkane, which is this right here, and we do NaCN DMSO. Do you remember what reaction this would do?
I want to say that the Na attacks the Br.
So the Na right here would be a full positive charge, which means that whatever is attached to it is fully negative charge. So the full negative charge here is Cn minus, which is the nucleophile.
Oh, right.
Right? The Cn minus is going to attack the carbon and then kick out the good leaving group bromine right there. Like that. Right? And that's going to give us this nitrile right here. The C triple bond N. Right? And do you remember how I wrote the nitrile as the cousin of the carboxylic acid derivatives? Like this is a family.
That one can be used to turn into the
carboxylic acid, right? Any of these carboxylic acid derivatives here can be converted back into the parent functional group carboxylic acid. Right. And there's a very specific name for that. Do you know the very specific name for that?
I don't remember.
It's okay. It's okay. It'll be hydrolysis.
Okay.
Hydrolysis, right? And that'll be done with water. Hydrolysis, like think of hydro, like water, right? So you're gonna add water in it, and it could either be done in acidic conditions or basic conditions. But because we have the neutral carboxylic acid, not the deprotonated version, the carboxylate, assume acidic conditions here, right? Okay. So to convert this nitrile into this carboxylic acid right here, right, where this pink carbon from the CN is going to be this pink carbon here of the carboxylic acid, and the yellow backbone 4 carbon is going to be this 4 carbon chain right there, like that, right? Okay. The reagents that would convert this nitrile into this carboxylic acid is going to be acid, H2SO4, water, and heat, right? These are the hydrolysis reagents here that would convert this nitrile functional group into this carboxylic acid functional group right there, right?
Okay.
So to summarize that's 2 reactions we just did. If we have this halocane which is gonna be 4 carbons long, there's 2 ways where we could expand that molecule by 1 carbon, which is gonna be the carboxylic acid, right? The first way that we went over is the Grignard reagent, so we have to do Mg ether to create the Grignard reagent. Second step, add the carbon dioxide, and then third step, acid workup. For the second route or second method, first step is do NaCN with some aprotic solvent if you want for SN2, and then once you get the nitrile, you do hydrolysis reaction to convert that nitrile into the carboxylic acid using acid, water, and heat, like that. Okay, so you could use either methods, either reactions to get from here to here, or to get from what was the synthesis problem? To get from here to here, right? So which one did you want to use, the Grignard reagent route or the hydrolysis of nitrile route?
I think the hydrolysis of the nitrile.
Okay, so let's use the hydrolysis of nitrile. We're going to do NaCN or KCN, both works, to convert this primary halocane into this nitrile functional group. And then once we have that nitrile functional group, we can convert this entire nitrile group into this carboxylic acid group using acid, water, and heat. Yep, hydrolysis reagents like that.
Okay.
Okay.
Is there a preference on like when some of these are like we can't use, we have to use like one or the other, like one's more preferable?
Yeah, it depends on the reactant molecule actually. In this reactant molecule here, it doesn't matter what method you use, right? But some reactant molecules will matter what you use, because let's say, for example, we have something like this, and we wanted to get to, let's say, this molecule here, where the alcohol stays the same, but we added an extra carbon, which is going to be this carbon right here, which is the extra one. So that's 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. The yellow is the similarities between the reactant and product molecules. if you try doing the Grignard reagent route, right, by doing, let's say, Mg ether, you're going to create the Grignard reagent, which is going to be this RMGBr right here, where you notice how this carbon here is partial negative or partial positive. I mean partial negative. It's not partial positive. It's partial negative.
Oh wait, sorry, you cut out. What were you asking?
Yeah. You know how the carbon here directly attached to the Mg or magnesium is partial negatively charged?
Yeah.
That's a strong nucleophile or strong base. If there is an acidic proton present, like the H here of the alcohol, what's that going to do is that it's going to do an acid-base reaction right away and deprotonate the alcohol to create that alkoxide ion right there. And the MgBr would dissolve away into ions like that.
Oh, okay.
Right? So we can't do the Grignard reagent route here because of the alcohol present in the molecule.
Okay, yeah, that makes sense. Thank
Right.
you.
Of course. But we can do the hydrolysis of nitrile route. Like you can do NaCN to create the nitrile here. And then from there, you can use acid, water, and heat to convert the nitrile into the carboxylic acid. Like there's no problem there.
Okay, that makes sense.
Right. But now let's say that we have an alkene present somewhere and we have a primary halocane and we want to create a carboxylic acid where like we added an extra carbon to the molecule and that extra carbon is the carboxylic acid carbon, right? If we try doing the NaCN route, like NaCN to convert the bromine into nitrile, and then we want to do hydrolysis. Let's add a methyl group here with H2SO4, water, and heat. From 118B, the alkene would also react with the acid and water to do a Markovnikov addition of an alcohol, like that.
Oh my gosh, I remember Markovnikov.
Yeah, the Markovnikov, the more substituted position of the alkene.
Yeah.
Flashbacks, right? That's a 118B reaction with an alkene, acid, and water. But we want to keep our alkene. We don't want to destroy our alkene. So to do that, we're gonna do the Grignard reagent route, right? Where we're gonna do first Mg with ether to convert the halocane into the Grignard reagent, which is this right here. And then from here, we could do CO2 to create the carboxylate ion. And then from here, we could do dilute H3O plus, dilute acid workup to protonate the carboxylate ion into the carboxylic acid right there. Like that. Okay?
Okay.
And then from this carboxylic acid right here, you can convert that into the most reactive carboxylic acid derivative using SOCO2 and T, which is the acyl halide. And then from there, you can create any of the other carboxylic acid derivatives in one step from this acyl halide right here. And that's very useful for synthesis problems right there.
Right.
Yeah. Which we just used in the problem that you sent me right here. Right.
Okay.
Like once we created that carboxylic acid here, we used SOCO2 with T or pyridine to create the acyl halide, and then we could create this amide right there in one step. Like that.
Right, and so like the SOCl2 is like basically the last, or like one of the last steps before turning it into like any of the carboxylic acid derivatives.
Yes. The SOCO2 would first create the most reactive derivative, and then from that point, the most reactive derivative, you can create any of the lower, less reactive derivatives in one step. Okay. Yep.
I was wondering. Oh, sorry.
Yeah. So that's the preferred way to create any of the derivatives, is to start from the most reactive derivative. It's the more efficient way in lab.
Okay, that makes
Yep.
sense. Thank you.
Yep.
And I was wondering if I could possibly see like the last reaction that we were working on with the ether, or I think it was like I think
Yeah.
you wrote it down.
Oh,
with
like
the-
here?
Oh yeah. Okay.
This one right here. You wanted to see this one right here?
Yes, please.
Yep. Yep. Okay.
Okay, got it.
Yep.
Thank you.
Yep. Of course. Okay. Amanda, did you have any thing you wanted to go over for Chem 118A Fahrenheit?
Could you go over like the staggered eclipse
Oh.
Gauss?
Yes, staggered eclipse Gauss Newman projections, those things.
Yeah.
From 118A? Yes. Okay. So, let's start off with drawing butane. How would you draw butane? In bond line form.
That was one carbon? Or
One
carbons?
would be methane. One carbon would be
Yeah.
methane, right? Two carbons would be ethane.
Mm-hmm.
Three carbons would be propane.
Oh, and 4 is butane.
Yep, four is butane. And then five would be pentane. Six would be hexane. Seven would be heptane. Eight would be octane. Nine would be nonane. And then 10 would be decane.
Mm-hmm.
Right? So butane in bond line structure would look like this right there, where each point or like each vertex represents a carbon, right? And these are the bonds to the carbons. And we know that for a carbon to be neutral, it has 4 bonds. If we look at this carbon right here, we see that it is bonded to 2 other carbons, one here and another here. But to be neutral, it has to have 2 more bonds, and those 2 other bonds are invisible bonds to hydrogen, right? The bonds to hydrogen are invisible. They are implied in bond line structure. Right. Okay. So now, how many invisible hydrogens is this carbon attached to right here? 3. Yes.
3.
Correct. Now, for Newman projections, right? It's just a way of looking at the molecule. Like bond line structure is different way of looking at butane. Like this is the bond line structure. Then let's say Kikuli structure. Right? It's just a different way of viewing the structure, like that. Right. Okay. Now let's say this is your eye, and you're looking down straight at this pink carbon right here, straight on. The carbon behind it is going to be a blue carbon right there. Because you're looking straight on at this pink carbon here, and the blue carbon is hiding behind it, this bond right here between the pink and blue carbon is invisible. Like you can't see it because the pink carbon is in front of it. Right? So now in Newman projection, this pink dot that I just drew out right here is that pink carbon that you see. So now imagine yourself like over here, and then you're looking down the molecule down this way, like your eyes are there, and you're looking down the molecule this way, right? You're looking at the pink carbon directly, which is this pink dot right there. Okay. Now, I'm gonna draw a blue circle behind the pink dot to represent this blue carbon. So the carbon behind the pink dot is gonna be this blue circle right there. That blue circle represents this blue carbon right here. Okay. Okay. So now let's see. This bond here we do not see, but what other three groups is this pink carbon attached to? We already drew the blue carbon, right? But what other three groups is the pink carbon attached to here?
Methyl group.
One methyl group and
Oh, and then two hydrogens.
two hydrogens. And the way that we're gonna draw that is to start from the pink carbon, and it doesn't matter where you draw the methyl group, right? But it's always gonna be like this, like a kind of like a peace sign, right? From the pink carbon, the three other groups it's attached to, right? You could start your methyl group here, here, or here. It doesn't matter, right? Let's say that the methyl group is on top. That means the other two groups are going to be hydrogens right there, like that. Okay. Now, if you look at the blue carbon, we already know that it's attached to the pink carbon, but that blue carbon is also attached to one methyl group and two hydrogen atoms like that, right? And let's say that this bond right here between the pink and blue carbon is the reference bond. You notice how the methyl group of the blue carbon is opposite or anti to the methyl group of the pink carbon right there?
Yeah.
That means that there have to be opposite on Newman projection as well. Because the methyl group here is going up on top of the pink carbon, if we want to draw the methyl group coming off of the blue carbon, it has to come out down this direction right there. Like that. Right. And I'm going to draw out two other bonds coming out of the blue carbon or the back carbon, like this, which is going to be attached to two hydrogens like that. And you notice how I draw out the bonds like as far away from each other as possible? I didn't draw the bonds like this or like that because like these would be way too close to each other. Yeah. This right here is called the staggered conformation because the bonds are far away from each other as possible. They're staggered from each other. Right. Okay. And now, what is the bulkiest group of the pink carbon? Ignoring like this bond and the blue carbon.
The methyl?
Yep, the methyl. And I'm going to highlight that methyl in yellow like that. What about the blue carbon? What's the bulkiest group coming off the blue carbon?
Methyl?
Also the methyl, right? Which I'm going to highlight in green right here. What is the angle between the two bulkiest groups in this Newman projection here?
180.
180, right? Which is directly opposite to each other. So this specific staggered conformation is going to be anti-conformation. Right? And that's a very good thing. It's very stable because there's less steric hindrance. Have you heard of that term, steric hindrance?
No, I don't think so.
So you will learn about it when you learn about energy and stability. Anti-conformation in Newman projection is the most stable Newman projection. Right? It's the most stable Newman projection because these two bulkiest groups here are not bumping into each other. That's steric hindrance. Steric hindrance is if the groups bump into each other. That's very bad. We don't want that, right? We want the groups as far away from each other as possible. Okay. So think of steric hindrance as just parts of a molecule touching each other, bumping into each other, like that. Okay. Okay. So now, you know how this is a single bond between the pink and blue carbon? Does it have free rotation? Can it rotate freely?
I believe so.
Yep, it can. So when we rotate that, the groups are gonna move, right? So imagine if you had a model kit and let's say you're holding the pink carbon and it's three groups, the methyl group and the two other hydrogens still. Like it's not gonna move. And then you rotate this bond right here between the pink and blue carbon. the methyl group, the hydrogen, and this hydrogen here is going to rotate around like that.
Mm-hmm.
Whereas these groups here on the pink carbon are going to stay the same. It's going to stay still. Right? So I'm going to draw that here. When we rotate the Newman projection, one group stays the same, which let's say it's going to be the pink carbon. The pink carbon here is going to have the exact same groups at the exact same spots. So the methyl group is going to be on top, and the two hydrogens are going to be to the left and right like that. But if I rotate 60 degrees clockwise, right? Let's look at this hydrogen right here. I'm going to rotate it until it goes behind this hydrogen right here, which is going to be something like that. And then this methyl group here is going to be behind this hydrogen right here. This hydrogen here is going to be behind that methyl group right there. And I'm going to highlight the bulkiest groups to keep track of everything. This is the yellow methyl group on the front carbon. This is going to be the green methyl group of the back carbon right there. And be careful of how you draw the groups coming out of the back carbon, right? Make sure to start it from the big circle. Don't start it from the center, like that. Like if you look at this green highlighted methyl group right here, it's coming off of the big circle right there, because that big circle represents the back carbon that we do not see, which is this one right here. Right. And I can highlight that.
Oh.
Like that's the green methyl, and this is the yellow methyl right there. Right.
Mm-hmm.
Okay. So does this make sense so far, Amanda? Like how I got to here?
Yeah. So the 1, 2, 3, 4. Oh, okay. So the methyl group, the green one, moved, and then
like all of these three groups moved right here. This green methyl group moved, this hydrogen moved, and this hydrogen moved. Everything that is attached to the back carbon, the big circle, moved 60 degrees clockwise.
yeah,
like,
but then
in
the front hydrogens from the pink carbon are in the same position. They stayed the same.
And the yellow methyl group coming from the front
And
carbon.
the yellow, yeah.
Yes.
Everything from the yellow one stayed the same.
Everything from the front carbon stays the same, and it's gonna stay the same all the time when we rotate the bond, because we're holding that part of the structure when we're rotating it, right? It's only gonna be the back carbon that changes when we rotate it. Okay. You can keep the back carbon the same, right? And then just rotate the front carbons. Some people do that, but it's easier for me to keep the front carbon the same and just move the back group carbons, like the back groups on the back carbon, right? Okay. So this right here, you notice how like the back group and the front group are like on top of each other, like they're so close to each other. They're eclipsing each other. That's the eclipse conformation. Eclipse conformation. They're eclipsing each other.
Oh, that makes sense. Like
right. And
like
that
the sun being behind the moon.
Yeah, like this, like the sun eclipsing behind the moon. That's like eclipse conformation, and that introduces something called torsional strain. Right, and it's torsional strain because the angle between them is not very good. Like they don't want to be in that awkward angle, right? Like this eclipse conformation here only exists for a very short amount of time. Like when you rotate the bond, this is a transition state, right? It's very high energy. It's very unstable, right? And it's very unstable because of this non-ideal torsional strain, right? Okay. Now let's do it again. Let's keep the front carbon the same. Does that make sense so far on why I drew that like the exact same way as the other ones, like and the front carbon? Like I'm keeping it at the same.
Yeah.
Right? Now the back carbon, which is this big circle right here, the green methyl is now going to be right here. So this is the yellow methyl. This is the green methyl right there. This is the hydrogen. This is the hydrogen right there. Okay. Okay. Now, does this make sense, Amanda, on how I got here? Like I rotated the back.
You rotated
carbons.
the back one again.
Yep.
Yeah.
60 degrees this way. Correct. And now, what conformation is it in? Staggered or eclipsed?
It's been staggered.
Staggered. Yes, it's staggered. And you notice how the bulkiest group on the front carbon, which is this yellow methyl group, and the bulkiest group on the back carbon, which is this green methyl group, they're right next to each other. They are adjacent to each other. They're gonna have steric hindrance. This right here, this symbol that I just drew out in red, is steric hindrance, which means that they're gonna touch each other. They're gonna bump into each other. Right? And that's not a good thing. That's gonna increase the energy, which means that it's gonna be less stable. Right. Okay. And now I'm gonna rotate that single bond again, keeping the front groups the same, and just rotating the groups on the back carbon like this, where this is the bulkiest group on the front carbon, this is the bulkiest group on the back carbon right there. Okay. Any questions on how I got to this point, Amanda?
No, I see it.
Yeah, because you're keeping everything in the front the same. You just rotate in the back carbons. Now this right here, what do you see? What do you notice about the two bulkiest groups? Where are they in relation to each other?
Like almost right next to each other.
Uh-huh.
They're right next to each other. Yeah, they're almost touching.
Yep, they have steric hindrance because they're right next to each other, and they also have torsional strain. Torsional strain comes from the eclipse structure.
Oh yeah.
Eclipsed structure because of that angle, that bond angle between them. Steric hindrance comes from the two bulkiest groups being right next to each other. Okay. Now I'm gonna rotate it again, keeping everything in the front the same to get this right here. And I'm gonna draw two more to complete the whole cycle. And then this is gonna be the last one right here. And I'm gonna highlight the yellow and green methyls. The yellow methyl stays the same throughout, which is gonna be on top of the front carbon. And then green methyl is gonna rotate 60 degrees at a time. Like that. Do you see how that's rotating, Amanda? Right? What is this conformation specifically? Right here. There's a specific name of this conformation right here. We could first start by determining if it is staggered or eclipsed.
I think it's staggered.
Correct. It's staggered because the bonds are as far away from each other as possible. They're not eclipsing or on top of each other. Now, for staggered, you can have anti-conformation, which means the two bulkiest groups are 180 degrees apart or opposite from each other, or gauche, which means that the two bulkiest groups are right next to each other, or somewhere in between, not gauche or anti. So is this Newman projection right here anti, gauche, or somewhere in between? Like,
Um,
to determine that, look at the relationship between the two bulkiest groups.
would it be gauche?
Yes, gauche. Gauche means that the two bulkiest groups, which is this and this, are right next to each other, which is gonna bump into each other and have steric hindrance, and that's gauche right there. Right. Staggered is an umbrella term, which includes gauche and anti. Okay. Now, if we rotate it again, would this be staggered or eclipsed? Confirmation right here.
Eclipsed.
Eclipsed, correct. Which has what kind of strain? There's a type of strain here.
Torsional.
Yep, torsional strain because of that
Torsional.
angle, that unwanted angle. Correct. Does it have steric hindrance here?
No.
No, right, because the bulkiest groups are not touching each other. They're from different areas of the molecule now. Right? Now, what about this last molecule over here when we rotated it again? When we made it 360 degree from the first molecule. What?
Anti.
Anti. It's
Staggered.
staggered, specifically anti. Right? And anti is the most stable Newman projection, which is gonna have the least energy. Right? Most stable, least energy. Because the bulkiest groups are far away from each other as possible, the least steric hindrance, they're not gonna bump into each other, and there's no torsional strain. Right? Okay. Did that help, Amanda, of how to see the Newman projections? That's good. That's good. Yeah. There's gonna be more to it, right? Like there's gonna be about ranking the stability. There's gonna be ranking the energy. And there's gonna be different ways of looking at it with like wedges and dashes. Like let's say for example, we have something like this with wedged ethyl group, and then we have a dashed tert-butyl group, and then your eye is gonna be right here, and then you're gonna look down this part of the molecule here, right? Which we can go over that example tomorrow, and I made a Kahoot with the problems that I had when I took the class online during COVID. So we could try that after I go over this example with you tomorrow, if you can show up, Amanda. That's good. That's good. Okay. Okay.
Thank you.
Yep. Of course, Amanda. Have a nice night. Okay. Elysia, did you want to do one more problem for 119C?
Please.
Let's do it. Let's do it.
Okay, let me screenshot it.
Okay. Okay. Look what I got, Elysia.
Oh, wait.
It's
Where is that from?
7 Leaves. It's a popular cafe at San Jose.
My roommate told me about that.
Dang. Is your roommate from San Jose too, or SoCal?
I'm from SoCal, so I think she knows of it.
Yeah. I think it started from SoCal and then it came over here to San Jose.
What did you end up getting?
I got mung bean milk tea.
Oh, that sounds good.
I know. I was thinking of matcha or mung bean, but I got mung bean instead.
Do you what do you think about it? Do you like it?
Yeah, I like it. It's so good.
Nice.
Yeah, this is
I've never tried.
You never tried?
No.
Oh,
but
shoot.
I've heard a lot of good things about it, so
I gotta put you on it. This is actually free.
One of these days when I go to San Jose.
Yeah.
Yeah,
it's free because it's my sister's birthday today, and then 7 Leaves gave her a free drink, and then she ordered it on her phone, and then I just picked it up at the store.
Wow, that's so exciting.
Yeah.
That's crazy. Is she going home this weekend too, or no?
Yeah, she is. She's
Nice.
going home this weekend. You are too?
No, I went home last weekend.
Mm-hmm. That's good.
Yeah, I celebrated then, and I need a lot.
Oh shoot! I think you cut off, Alicia. You what did you
Oh,
celebrate
shoot.
back home?
Oh yeah, it was my birthday last weekend, so I ended up
Oh,
celebrating then.
dang! Happy birthday, Alicia.
Thank you.
Yes, 20, right? 20 years old.
Yeah, 20. So
20.
sad.
Wait, that's crazy. You just turned 20?
Yeah, I'm an old now.
No, that's young. What?
I don't know.
Dang. That's crazy to think about how you just turned 20 before like you were like 19, 18. Oh my God.
I know, that's so crazy. You've
I-
been here since, like for what? That's been 2 years?
yeah.
Yeah, basically 2 years.
Yeah. When I tutored you in Gen Chem, like Chem 2C, were you
That was
18?
like the end. Yeah.
You were 18 at the time?
Yeah, or
Oh.
Gen Chem. Wait, oh, that was for C?
Yeah,
I
Chem
think that was in the
2C.
spring. So yeah, I think I was 18 or 19. I forgot.
18, 19. Yeah, yeah. Dang.
That's crazy.
I know. I feel old now.
You're
Yeah.
not really that old.
I know, I know. My birthday's coming up next month, November 16th.
Yo, so
Yes.
yours is like basically after your sister's.
Yeah, a
You
month
guys are like
after.
close. You guys are
Right.
like,
Yeah.
would that still be considered fall?
Fall? Yeah, yeah.
Yeah, you guys are like fall babies.
Uh-huh. Uh-huh. So
Wow,
you're
that's
Libra. You're a Libra.
yes, I am.
Yeah.
Wait, so then and then that means your sister's also Libra, right?
Yeah, she is. She is. Yeah.
Ooh. Yeah.
Let's do this. Okay. I'm turning 23. 23 next month.
Wait, only 23?
Yeah, how old did you think I was?
Um,
20 what?
well, I think cuz you graduated in wait, like would that be 2 years ago?
Oh, no, I graduated last year. 2024.
Oh, wait, okay.
Uh-huh. Yeah, did you think I was like 25 or something?
No, I'm not 25 because I know you just graduated, but I thought you were like 22.
Oh, 22. Yeah, yeah.
21.
Uh-huh. Dang. Oh, so you thought I was younger.
Just slightly, yeah.
Yeah. Uh-huh. Okay, so for this synthesis problem over here, let's do the same thing. Let's find the similarities.
Right.
This right here, which I'm highlighting in yellow, is going to be the same exact structure as this highlighted in yellow right there, like that. Let's make sure by counting the carbons, like from the left carbon, that's 1. This is 2. This is 3. This is 4. This is 5. This is 6. Let's make sure that's 6. 1, 2, 3, 4, 5, 6. It's 6, so it matches out, right? And we know this is
Right.
2 because like this carbon 2 here, like has these 2 alkyl groups coming off of it, like that. We see that the alcohol is no longer there from the reactant molecule, right? And
Yeah, it looks like it was used to turn
Uh-huh.
into like an O minus maybe.
Uh-huh. So we see, what is this functional group right here?
Isn't it an ether?
Oh, so it would be an ether if this carbonyl is not there. Like if that
Oh,
carbon
sorry,
number 1
ester.
oxygen, ester, yes. And
Yeah.
ester is it belongs to what family?
Isn't it the carboxylic?
Acid
Yeah.
derivatives, right? Which is gonna be right here. And it's less reactive than the acyl halide. So what is one way that we talked about that can create an ester very quickly in one step?
Well, we would be using SOCl2, but that's like in the last step. But we could either use Grignard or NaCN.
NaCN. That's if we have a good living group present, right?
Oh, right.
Like a haloalkane or
But we
something like
don't.
that. We don't. Like, remember the very first thing you said? Like when I asked you how to create that carboxylic acid, you said Jones.
Yeah.
What did we need to use Jones? What kind of alcohol? Primary, secondary, or tertiary?
Primary.
Primary. Do we have a primary alcohol here?
Oh, we do.
We do.
Yeah.
So we could use Jones
then we
here,
could-
but Levens won't say Jones in her like answer choices, should use something with chromium and oxygens, like H2CrO4, H2SO4, water, or Cr2O7, H2SO4, water, something like that. Something with chromium and lots of oxygens is Jones reagent right there.
So like, would CrO3 be acceptable
Yeah.
as well?
CrO3 is another one, or
Okay.
CrO3, H2SO4, H2O. Yep, that would be also be Jones, chromium and oxygens like that. Right.
Okay, and then like going back to like the other method that we were saying that we can use the what was it, the second method?
Uh-huh.
I didn't see like an NaCN, so do you think like KCN would also work?
Yeah, KCN would also work because
Okay.
that would be the exact same thing as NaCN, just a different spectator ion. Like Na and K are both positively charged, but the important thing here is the Cn minus.
Right. Okay, that makes sense.
Yep. Okay. Now once you have this carboxylic acid over here, you notice how we could like turn this carboxylic acid into the ester by like first doing SOCO2 and then putting an alcohol there, which is the alcohol R group is gonna match the OR group of the ester. We're not gonna do that yet because you notice how we have an extra group here, like
Yeah.
next to this ester, right? This carbonyl carbon here is gonna be called the carbonyl carbon. The carbon next to it is the alpha carbon, and then after that is the beta carbon, and then gamma, delta, epsilon. If you see something alpha to this carbonyl carbon right here, there's a specific reaction that would add a bromine there, right? And that's called the Hell-Volhard-Zelinsky reaction, HVZ reaction, right? And the reagent for that would be NaOH, Br2, and water. Let me double check that to be sure before I move on.
Okay.
Hell-Volhard-Zelinsky reaction, HVZ reaction. Okay. Oh no, these reagents are Hoffman rearrangement. That's a totally different reagent for a different reaction.
Yeah.
Right. So it's gonna be PBr3 trace Br2 first step, and then second step could be like water. Like use the HVZ reaction reagents that Levins taught you. Hell-Volhard-Zelinsky, right? And what that would do is that would add a bromine alpha to the carboxylic acid, like that. Okay. Now, you notice how this is an ester right here, where this is an extra carbon.
Yeah.
Now we can use one of the methods to create the extra carbon. Do you want to use the Grignard reagent or the hydrolysis of nitrile? There's one way that would only work here.
I want to try Grignard.
Grignard. So if we tried adding Grignard, right, with Mg, what would be the charge of this carbon here?
Oh, would it would make it positive.
So it is positive right now without the Mg, but if this is MgBr, it would be partial negative charge. Yeah.
Okay.
And then that would be a strong nucleophile or strong base. And you know how we have an acid present here, which is this acidic proton?
Oh, it's gonna wanna go to it and then create an O minus.
Yes. And we don't want that. We don't want to destroy this carboxylic acid. We don't want this O minus right here. Right? So we can't do Grignard because there's an acid there. So that's the problem. Right.
Okay.
So we could do KCN or NaCN to convert the Br into the nitrile CN. And then how can we convert that CN into carboxylic acid?
We would use the S SOCl2 and T.
Oh, that's gonna convert the carboxylic acids into acyl halide,
Oh.
like that.
Okay.
But we want to convert this nitrile into the carboxylic acid with hydrolysis, which is gonna be done through H2SO4, H2O, and heat.
And heat. Okay.
Right. That's hydrolysis, and that doesn't interfere with the carboxylic acid because that's an acid, and we're putting it through acidic conditions, so that won't affect the acid right there. Nothing's gonna happen to the acid.
Okay, that makes much sense.
Right. This right here is gonna affect the nitrile because it's gonna convert the nitrile into the carboxylic acid right there. Right. And then once we have our 2 carboxylic acids, that's when we do the SOCO2 and T, which will convert the carboxylic acids into what functional group?
It would connect to
Like, what would these carboxylic acids here convert into if we use SOCO2 and T?
it would convert into the most reactive derivative, and then then we get our least reactive that we want.
Yep, it will convert to the most reactive derivative, which is the acyl halide. And this is not the least reactive one, it's the ester, which is one of the less reactive ones. And to do that, you notice how this is the leaving group of the ester right there?
Yes.
We're gonna use that exact same leaving group of the ester, but add an extra H to make that alcohol right there. And this is gonna be in at least 2 equivalents, one for each, one there and one there. But just assume this is an excess right there.
Okay.
Yeah.
And then like going back to like with the when we used like from the other problem when we used like NaCN or like KCN, that would be like an SN2 mechanism, right?
Yeah, SN2 mechanism because NaCN or KCN will have a CN minus nucleophile, and then that's gonna attack this electrophilic carbon, kick out the good leaving group to substitute it with the nucleophile CN.
And then like later on, after it's like converted to the carboxylic acid, and then we're using
SOCO2?
Yeah. Would there be a workup?
Acid workup? No, there won't be acid workup from here.
Okay.
Yep, no acid workup for this mechanism.
Or like when we use with H2O and NaOH and heat.
Oh, this one right here?
Yeah. Is there gonna be a workup?
There's no acid workup because we're already in acidic conditions with the H2SO4. Right? In the previous example, when we did Grignard reagent, that's in basic conditions, right? Because a Grignard reagent is a strong base, strong nucleophile. When we have this Grignard reagent react with the CO2, it ended with a deprotonated carboxylic acid, which is a carboxylate, right? Which, if we wanted to convert that into the neutral carboxylic acid, we needed an acid workup step right here.
Okay, I see what you mean.
Right. So in basic conditions, you would need an acid workup if you want to get the neutral carboxylic acid. But in acidic conditions, you don't need acid workup because the acid workup is included in the acidic.
Okay, because I was like looking back and like working through like what we were like determining for like that other question for the mechanism.
Yeah.
Or like 16. And like later on it's like stating that there's like a workup, which like I'm kind of confused. I can show you what like I have. I mean, most of it is like you have to like translate it to like
the mechanism.
Yeah.
Yeah.
Let me send it to you real quick. Okay, and then that one, and then this.
carboxylic acid group by using Q directly to form a or by using you know how it says or by using reagent something?
Yeah.
That or is gonna be the Grignard reagent. So the alternative method is the Mg ether to convert the haloalkane into the Grignard reagent, and then you do CO2 to get the carboxylate ion, and then to get to the carboxylic acid, that's when you do the acid workup. Okay, so the
Yeah.
acid workup would be from the Grignard reagent, not the NaCN or KCN method. Yeah.
I think like what it was like confusing to me was like when I was like trying to pair the Mg with like something because I didn't see Grignard, so like I don't know. It was like weird. I was like trying to translate which reactants I was using.
Did you see Mg ether? This one right here on the answer choices. It should be somewhere there.
I saw just I just saw Mg alone.
Yeah,
then
yeah.
I pair with an ether.
Oh, right, with the solvent. Yeah, we could look at it tomorrow. And I could send you something that might help after this. But yeah, let's look at it tomorrow. Yeah.
Oh no, sorry, I froze.
Yeah. Hello.
Oh wait, okay. I
Yeah.
think I had unstable network again. Sorry.
Oh, it's okay.
But I was wondering if I could see the other one. Hang
on. See the other one? This one right here?
Yeah, with
This one?
Yeah. Okay.
Yeah, and then we could look at it again tomorrow, and I'll send you something after the session that might help. Yeah.
Okay, thank you so much. Thank you.
Yep. Of course, Alicia. Good night. Oh,
Good
wait,
night. See ya.
Yeah, you were cutting off. Oh, wait, did you say?
Oh my gosh. Sorry.
No, it's okay.
It's really bad.
Yeah.
But thank you so much.
Of course, Alicia. Of course. Yeah.
Have a good night.
You too. Good night.